Everybody, thank you to be here. So, vamos a iniciar este taller de trabajo. También queremos agradecer la presencia del doctor José Manuel de Cevmf, y la presencia nos acompaña también el ingeniero José Manuel Caso. Él es el gerente de la CONAFOR en el estado de Jalisco. Entonces, pues estamos todos. La verdad es que el día de hoy es un poquito complicado. Hay una serie de actividades allá en la CONAFOR, y también estamos en un proceso de algunas áreas operativas, Manolo, están terminando el proceso de dictaminación para el otorgamiento de recursos, particularmente para el tema de compensación ambiental. Traemos los tiempos encima porque hay estados donde hay veda electoral, donde hay elecciones. Entonces, por discusiones gubernamentales no se puede hacer, digamos, la distribución o los pagos de estos recursos. Cuestión que empieza ya el 1 de abril, ¿no? Estamos trabajando más esforzadas. En fin, pues les agradezco a todos, ingeniero José Manuel Caso, gracias por recibirnos. Ahora mismo estamos en las instalaciones de la gerencia estatal, ¿no? Y el día de mañana vamos a regresar a las oficinas de la CONAFOR. Así es que, pues dispongámonos a tener un excelente día de trabajo. Yo voy a pedirles aquí a todos los otros que nos presentemos. Por supuesto que les queremos que nuestros invitados también se presenten, y sobre todo que nos sintamos con la libertad. El día de hoy estamos entre amigos, entre compañeros, entre colegas. Entonces, pues, es una reunión de trabajo. Entonces aprovechemos la presencia y la estancia de todos ustedes, ¿no? Entonces, quisiera pasar a la etapa de presentación, y por razones también, digamos, de la oportunidad que tenemos de estar en este lugar el día de hoy, pues a nuestro anfitrión, que es el ingeniero Caso, también pedirle y que comentar algo al respecto. Y después despediríamos, empezamos una etapa de presentación, que rompiéramos el hielo, ¿no? Hay servicio de cafetería, por favor, a la hora que gusten, pueden pasar por tomar una fruta, ¿no? En toda confianza. Entonces, ingenieros, también yo me voy a tener que retirar en unos momentos, pero pues quiero agradecer su hospitalidad, ¿no?
Buenos días a todos, bienvenidos sean todos ustedes. La gerencia de CONAFOR en Jalisco se honra con su presencia. Sabemos que estos eventos, este taller, tiene una finalidad en donde vamos a poder tener los conocimientos, las estrategias, la información necesaria para desarrollar mejor nuestro trabajo, y no nada más aquí en Jalisco, sino en todo México. Sean bienvenidos nuevamente, estamos a sus órdenes, y que sea enhorabuena para todos ustedes este taller. Gracias.
Gracias, ingeniero. Y también de la misma manera aquí el doctor Canto. El doctor Canto, hemos venido a hacer un trabajo extraordinario desde siempre con Cevmf, ¿no? Yo también quisiera agradecer, también que le haga llegar nuestro agradecimiento a Reini. Estamos en proyectos, en diferentes proyectos, y estamos comentando aquí un poco algunas de las cosas que están también, se están trabajando de manera conjunta. Así es que junto con él estamos haciendo este esfuerzo con el Servicio Forestal, el Servicio de Estados Unidos, la USAID, y por supuesto con nuestros amigos de la Alianza Cevmf. Entonces, vamos a comentarme y después pasamos ya a la presentación de todos nosotros.
Muchas gracias, doctor Serrano, ingeniero Caso, por recibirnos en las instalaciones de la gerencia estatal. Y pues como bien comenta el doctor Serrano, este es un taller cuya intención es dar a conocer los resultados del trabajo de 5 años de la Alianza México-Red en el componente de reporte de verificación. Y como se mencionaba, pues queremos que sea un diálogo más que una presentación, porque tenemos resultados muy interesantes para los cuales necesitamos su ayuda para tener una correcta interpretación y obviamente proyectar los siguientes pasos de lo que sucederá en el corto y mediano plazo. Entonces, pues nada, agradecer mucho su presencia, su participación y procedamos a las presentaciones.
Muy bien. Pues, ¿por qué no empezamos con nuestros invitados? Alexander Becini.
Sí, muy gracias. Mi nombre es Alessandro Bacini, and I'm one of the scientists at the Woodshole Research Center in the US. My background is in forestry, actually, and in the past 10 years, I've been working trying to use satellite data in combination with forest inventory and with forestry information to generate maps of the biomass, the above ground biomass distributions for tropical forests. And my work, together with my colleagues here, has been focusing from local scale to very large area pan-tropical scale. I'm very pleased to be here again. It's been a great experience to work as part of the MRED for the past 5 years, and thank you for hosting us today and giving us the opportunity to sort of share what we learned and what we sort of achieved in these past 4 or 5 years. Thank you.
Thank you, Alexander. Bueno, ya confianza en Alex. Perdón. Sorry.
Buenos días a todos. My name is Wayne Walker. I'm also a scientist at the Woodshole Research Center. I work very closely with Alessandro. My background is also in forestry and forest ecology and sensing. And like Alessandro, my work involves applications of remotely sensed data, satellite data, aircraft data, to mapping and monitoring forests. It's a great pleasure to be here, to have this opportunity to speak with you. Thank you so much, Conafort, for hosting us. And we look forward to really having a conversation with you about some of the work we've done over the past 5 years and potentially how it might be brought to bear to benefit what you all are doing here in the country. So thank you.
Thank you. ¿Sí dije mi nombre? ¿Sí, verdad? Bueno, ustedes sí, pero ellos. Bueno, tú también, Manolo.
Bueno, pues mi nombre es Manolo Campos, la mayoría de ustedes me conocen. Yo tengo el gusto de coordinar el componente de monitoreo, reporte y verificación de la Alianza México-Red. Y en conjunto con The Nature Conservancy y el Woodshole Research Center, hemos llevado la investigación en RD que complementa los esfuerzos de la CONAFOR, la CONADIO y el INED. Muchas gracias por recibirnos.
Gracias. My name is Enrique Serrano. Actually, I am the General Coordinator of Planning and Information in CONAFOR. And also I am a forester originally. Right now I don't know what I am. I really made that forest.
Mi nombre es José Manuel Caso, gerente de CONAFOR en Jalisco. Tengo la fortuna de ser ingeniero forestal de la Universidad de Chapingo. Entiendo un poco el tema y actualmente, como les decía, me desempeño aquí en Jalisco. Tenemos un gran reto. Jalisco es uno de los 5 estados de la estrategia de red más. Entonces, para nosotros es importante este evento y con gusto estaremos aquí al pendiente.
Muchas gracias. Están llegando los compañeros, por favor, fíjense, pongan su confianza. Hay un espacio de ustedes. Muy bien. Pasen el paso. Perfecto. Okay.
Good morning. My name is Richard Houghton, or Steve Houghton. It's the first time I've been here in this part of the country, but for a long time I have been looking at what it is that land management does for emissions or removal of carbon from the atmosphere. That I was trained as an ecologist, but for many years now I've been looking at how land use globally affects emissions of carbon dioxide and what that effect is for climate. It's good to be here. I look forward to these next couple of days. Thank you.
Buenos días, mi nombre es Sergio, trabajo en la Agencia del Sistema Nacional de Monitoreo Forestal en un área que básicamente se encarga de diseñar las metodologías de campo e implementarlas a nivel nacional. También estoy encargado de un proyecto de llenar vacíos de información en campo en el Inventario Nacional Forestal de Suelos, especialmente en áreas inaccesibles. Básicamente trabajamos con modelos a partir de datos de campo en la primera etapa. La segunda etapa sería usarlo con sensores remotos o alguna otra herramienta, y también apoyamos en el control de calidad de los datos de campo. Gracias.
Let me tell you, Sergio is also the specialist on manual. If you want to know something about it, just ask me.
Sí, bueno, como complemento a lo que decía el doctor, sí, tenemos un área dedicada exclusivamente a lo que son humedales costeros. Trabajamos en, digamos, modificar un poco la metodología para cachar un poco más sobre los diferentes ecotipos de mangle que tenemos en el país, ¿no? Y también estamos tratando de diseñar un sistema de monitoreo conjunto entre Estados Unidos y México para poder realizar un pequeño reporte de tipo PAO.
Buenos días, soy Raúl Rodríguez Franco, estoy a cargo de la gerencia del Sistema Nacional de Monitoreo Forestal. Recientemente esta gerencia migró, era antes la gerencia del Inventario Nacional Forestal y de Suelos, y Geomática. Y bueno, ahora nos toca también coordinar el trabajo que realizó el proyecto México-Noruega, y que ahora, con apoyo de la Unidad Técnica Especializada en MRB, estamos trabajando. Bueno, pues es un tema muy importante. Ahora se está trabajando también la Estrategia Nacional RED, más que lleva la misma coordinación. Nos toca la parte técnica, aportar todos los insumos para que se generen políticas y acciones que ayuden a mitigar los efectos de efecto invernadero. Entonces, pues les agradecemos toda la información que ustedes nos puedan compartir, sus metodologías, para ver cómo podemos también nosotros implementar aquí en nuestro trabajo.
One comment. Hace 2 días se aprobó una nueva ley forestal en México y se introduce en el texto de esta nueva ley el Sistema Nacional de Monitoreo Forestal como un instrumento de política forestal. Y además establece que es la CONAFOR la que está obligada a desarrollar ese sistema. Afortunadamente, para nosotros, el sistema ya casi está listo. Aunque tenemos un año para implementarlo de acuerdo a la nueva ley, pero casi estamos ya en eso. De hecho, la gerencia de inventarios que ahora se llama la Gerencia del Sistema Nacional de Monitoreo Forestal. Y bueno, ahí viene el MRB, ahí viene Barmex, ahí viene el Inventario Nacional Forestal, viene inventarios estatales, o sea, es todo una regla, una sombrilla, ¿no? Ahí cabe esto dentro de esta nueva gerencia y dentro de este precepto de ley que es obligatorio ahora ya para el país. Perdón.
Muy buenos días a todos. Mi nombre es Tania Salgado Ojeda. Yo vengo de la Gerencia de Manejo del Fuego. Soy enlace de información estadística de incendios forestales extinguidos.
Hola a todos, les habla su amigo Adrián Ochoa. Estoy en la unidad técnica especializada en monitoreo de protección.
nombre es Osvaldo Carrillo. Actualmente soy titular de la unidad técnica especializada en monitoreo, reporte y verificación, que es la versión institucionalizada de lo que fue el proyecto México-Noruega y que forma parte ahora de la gerencia del Sistema Nacional de Monitoreo Forestal.
Buenos días, soy César Robles, estoy en la jefatura del Departamento de las Coordinaciones Centro-Regionales y estoy a cargo de la estadística. En este momento, ahí en la gerencia del manejo del fuego, tratamos de cada semana calcular las emisiones de carbono mediante una ecuación que se formuló en el plan intergubernamental de cambio climático. Y pues bueno, nos mandaron para ver qué otras ideas podemos llevar ahí a la gerencia del manejo del fuego.
Muy buenos días, mi nombre es Jonathan Hernández, vengo de oficinas centrales del área de restauración forestal. Estoy a cargo de un proyecto supervisando de zonas áridas y semiáridas, que realmente igualmente venimos a mi compañía para que podamos hacer.
Muy buen día, mi nombre es Joel Marcos, de la Gerencia de Restauración Forestal, del área de compensación ambiental. Espero en este taller recopilar, tener elementos que nos permitan a nosotros evaluar lo que es la parte desde un diagnóstico hasta la evaluación de todo el proceso de restauración, ya que nuestros proyectos van desde 3 hasta 6 años. Entonces, permite evaluar en el tiempo los cambios que se pueden tener.
Buenos días, mi nombre es Ernesto Díaz Ponce, soy coordinador de programas del Centro de Excelencia Virtual en Monitoreo Forestal en Mesoamérica. Alargo el nombre. Y bueno, estamos aquí por parte del Centro de Excelencia como parte de nuestra función para difundir este tipo de experiencias y compartirlas con otros expertos que no pudieron estar aquí. Y finalmente, pues documentar el evento para referencias futuras y que estas buenas experiencias y prácticas puedan documentarse y ser difundidas. Bienvenidos.
Buenos días, soy María Ramírez Salgado, estoy en el área de teledetección de la Alianza del Sistema Nacional de Monitoreo.
Buenos días, Miguel Ángel Rosas, también de la misma área de teledetección. Soy geógrafo de profesión y me encargo también de realizar tareas de climática.
Buenos días, mi nombre es Miriam Vargas. Yo estoy en la unidad técnica especializada en MRB, como especialista en fortalecimiento de capacidades estatales en MRB, y doy apoyo por parte del Servicio Forestal.
Sí, buenos días, mi nombre es Eder Larios, soy responsable de reporte y registro de la unidad técnica especializada en monitoreo, reporte y verificación de la Gerencia del Sistema Nacional de Monitoreo Forestal. Solo para comentarles rápidamente, como país tenemos varios compromisos de reporte en este año y en el próximo. El Inventario Nacional de Emisiones de Gases de Efecto Invernadero como parte de la sexta comunicación nacional de la Convención. El anexo técnico del BUR, que es Biennial Update Report, que es el reporte de pago por resultados, ¿no? Actualizar los niveles de referencia, tanto a nivel nacional como a nivel subnacional, una serie de reportes bastante importantes como país.
Buenos días, mi nombre es Juan María Chávez González. Estoy encargada del área de informática de la Gerencia de Sanidad. Estamos ahorita implementando un sistema de alerta temprana. Dentro de uno de sus elementos es la generación de mapas de alerta temprana y evaluación de riesgo de ataque de diferentes plagas y enfermedades. Entonces estamos en proceso de la implementación de este sistema y pues todo lo que aquí se aprenda o se exponga, pues es de mucho interés también para poder desarrollar o seguir desarrollando este conocimiento.
Buenos días, mi nombre es Rubí Cuenca y también estoy en la Gerencia del Sistema Nacional de Monitoreo Forestal en el área de análisis e información. En este momento estamos preparando el reporte de resultados del segundo ciclo del inventario. Entonces estamos generando todos los indicadores forestales que derivan de la información que se levanta en campo. Y bueno, eso junto con el área de base de datos apoyamos en la revisión de la consistencia de los datos para tener pues estimaciones o información.
Gracias, muy buenos días. Mi nombre es Carmen Meneses. Soy realmente ingeniero agrometeorologista con una maestría en manejo forestal sustentable y tengo aproximadamente unos 20 años trabajando en programas remotos con sensores remotos aplicados en el tema de forestal. Estoy a cargo ahorita de los datos de actividad de la unidad técnica especializada en MRB, que está adscrita a la Agencia del Sistema Nacional de Monitoreo Forestal. Y mi quehacer, bueno, tengo varios retos, un poco es generar realmente un sistema satelital que permita llevar a cabo con un monitoreo que pueda responder a las necesidades de los reportes internacionales, que tenga buenas actitudes, que sea completo y que se apegue a la definición que tenemos como país de bosques. Muchas gracias.
Buenos días a todos, mi nombre es Edgar Martínez, yo soy el webmaster del Centro de Excelencia Virtual en Monitoreo Forestal. Estamos aquí apoyando para que esté grabado y transmitido en vivo también.
Muchas gracias. ¿Qué falta aquí atrás? ¿Nadie más? No. Ok. Muy bien, pues sin más vamos a dar inicio a los trabajos de este día. Y aquí les vamos a pedir, voy a pedir aquí a Manolo Calvo que nos guíe. Nosotros vamos a salir en unos segundos, en unos minutos, pero si podemos regresamos. Y si no, nos vemos el día de mañana, allá ¿no? Muy bien, pues adelante Manolo, gracias nuevamente ingeniero Paso. Y bueno, empezamos con la agenda del día, ¿no? Entonces, por favor, Manolo, si nos puedes guiar en esta parte.
Muy bien, pues gracias. Tenemos 4 grandes temas en la agenda de este taller. Y los primeros 2 que tocaremos el día de hoy es como la tecnología LiDAR. La tecnología LiDAR puede ayudarnos en estos sitios con poca accesibilidad para el inventario forestal, nacional forestal y de suelos. Y también veremos el producto de cambio, de Woodshole Research Center, que va asociado al mapa de biomasa, que es para el año 2015. El día de mañana compartiremos los avances y resultados preliminares de una propuesta de modelado de flujos de carbono, es el Bookkeeping Model del Dr. Clinton. Y el Dr. Michael Schmidt nos estará acompañando para presentar el mapa de alta resolución para la península de Yucatán, que es un insumo clave para el sistema MAPNEX. Y terminaremos presentando la propuesta de PNC para tener un mapa de zonificación productiva sustentable a nivel nacional, que justamente ayer presentamos en las oficinas del Dr. José Sarucán. Esta versión del mapa ya existe para la península de Yucatán y la intención es llevarlo a una escala nacional. En cualquier momento, por favor, las preguntas, las intervenciones son bienvenidas. Creo que la intención de tener este diálogo es ir más allá de lo que hicimos el año pasado con la primera fase de este taller. Y pues sin más preámbulo, le cedo la palabra al Dr. Weinberg.
Thank you so much, Manolo. I am going to make my way to the front of the room. And we can bring up
this one, intro to LiDAR. This one or this one?
Okay. I am going to be talking about LiDAR remote sensing for forest management and monitoring in Mexico. As many of you are probably aware, as part of the MRED project, we had we sponsored an airborne LiDAR initiative. So this presentation is going to review, among other things, the accomplishments that we've made in the context of this airborne LiDAR initiative, provide you with some of our results, and give you a sense for how this information could be used now and potentially into the future where forest management monitoring in Mexico is concerned. Now, I realize that we have a range of individuals here with a variety of different expertise. Some of you are remote sensors, some of you are foresters, some of you have expertise in measurement and monitoring. So I'm going to begin my presentation by giving you sort of a brief background on what LiDAR is and how it works, so that we can all get on the same page in terms of our understanding of this technology. So for those of you who already know a bit about LiDAR, please bear with me. For those of you who don't know a great deal about LiDAR, I hope you come away with this portion of the presentation having learned something. There are parts of it that are a bit technical. I will do my best to keep those technical portions to a minimum. By all means, though, if you have questions, I'd like to keep this informal. Don't hesitate to interrupt me, and I'd be happy to take your questions and try to explain whatever I can. So, first slide, please. All right, so this is going to be the introduction to LiDAR technology and systems. More of a technical background, please. So, just a brief outline. First of all, I'm going to talk about what is LiDAR. Okay, for those of you that don't know, how does LiDAR work? And then I'll move into applications of airborne LiDAR. Please. Okay, so LiDAR is an acronym. It stands for Light Detection and Ranging. It's also known by many other names, some of which include laser altimetry, airborne laser scanning, airborne laser terrain mapping. Okay, there are many different names. There are many different types of LiDAR. Okay. First of all, there's spaceborne LiDAR. Now, spaceborne LiDAR is not that common. It's a technology that we've used, Alessandro and myself. But it's not that common, and in fact, right now, I'm not sure that there is. There will be future spaceborne LiDARs. I'm not sure right now if there, in fact, is one operational. The bulk of my presentation is going to focus, however, on airborne LiDAR. That is, LiDAR carried on board traditional aircraft. Next. Now, in addition to airborne LiDAR and spaceborne LiDAR, increasingly LiDARs are being carried on board UAVs or drones. Okay, this is more of an experimental type system. Increasingly, people are testing this. There are a lot of issues associated with it, a lot of constraints that I think need to be overcome. I'll talk a little bit about those more later on. But I do think that this is an important potential technology that we all need to be aware of in the coming months and years. There could be a value here in Mexico. Next. And finally, there's also terrestrial LiDAR. Now, terrestrial LiDAR, which I won't be saying much about, operates very similar to these other forms of LiDAR. The difference is it's not carried on board some sort of aircraft or spacecraft. It's actually a LiDAR that's mounted on a tripod like this one. Okay? But it essentially operates in based on the same general principles. So, there are these four different types, and as I said, I'm going to be focused on airborne LiDAR. Okay. I'd like to begin with an example of some data so that we can start by getting a sense for what these data actually look like. This is an image from a forested hill slope in Oaxaca. And this is actually not a photograph. or an orthophotograph, or satellite data, or aircraft data. This is actually a three-dimensional LiDAR point cloud. Okay? This image, if we were to zoom in on it, is actually made up of millions and millions of individual points, okay, in space. And I want you to focus right now on these two trees. Okay? Next. These are two likely oak trees growing by themselves out in the open in the middle of that field. And we're now looking down on them, and we're looking down on this point cloud. Okay? And you can begin to see, I don't know how easy it is to see from back of the room, but you can begin to see that this image is made up of individual points. Okay, next. All right, here's a larger version of it. There are roughly 100,000 points that make up this image. Now this image is 60 meters by 60 meters. Okay, for those of you who are remote sensors or GIS analysts and work with Landsat data, you will recognize that this is roughly 2 Landsat pixels by 2 Landsat pixels. Okay, relatively small. And when we're dealing with data like Landsat, we have multiple bands associated with Landsat imagery. For an individual pixel, we would have maybe 6 or 7 different bands of information. And so for 4 pixels, we would have, let's say, 7 bands times 4 pixels. That would be 28 individual pieces of information for these 4 pixels. Okay? Now compare that to the 100,000 pieces of information that we have with LiDAR. All right? Next. Now, for example, we can color these points based on their height. The height in this particular point cloud ranges from 0, which is the ground, shown in blue, to 28 meters, which is the tops of these trees. Okay? Next. Now, if we turn this point cloud on its side, you can get a better sense of the point cloud in 3 dimensions. Okay, we can turn this, we can rotate it, and we can now begin to see the individual points that make up the image. Here again is the ground. Here are these 2 trees from 0 to 28 meters tall. Okay? You can see beneath each tree there's a bit of a shadow. And that shadow is simply the result of the fact that the energy, the electromagnetic energy coming from the LiDAR, doesn't completely penetrate to the ground right beneath the tree because the crown is dense, okay, and it's occluding the energy. Okay, so that's what that is. That's just a shadow where you're not getting returns. Next. Okay, so giving you a brief sense for what these data look like. Now I'm going to talk a little bit more about how it works. How does the LiDAR work? Okay. So what are the components of a LiDAR system? Well, there's 4 main components. There's a laser scanner, there's a GPS, there's an inertial navigation system, there's an onboard computer. And I'm going to talk about each of these a little bit separately, so you get a sense for the role that they have to play in the system. Next. Okay, first of all, there's a laser scanner. This, of course, is the most important piece of equipment. And it's important to appreciate what makes a laser different or unique from any other type of electromagnetic energy that we might use. Okay? LiDAR is an active system, so it's actually sending out, it's actually generating its own electromagnetic energy, it's sending it out, and that energy is interacting with the terrain and then being returned to the sensor. Okay? And that energy comes in the form of laser light. Okay? And laser is also an acronym. The acronym is here. We don't need to be so concerned with what the words in that acronym mean. But what's important to understand is what makes a laser a laser. Okay? Now I'm holding a laser in my hand, right? A laser pointer. You've all seen them before. Okay? And
And they have three important characteristics compared to any other form of light that we might be used to. First of all, they're monochromatic. That is, they're one color. You can see that in this case, it's red. Okay, a single color. Lasers are coherent. Okay, coherent meaning the waves are all in phase. You can see that here. These waves are all in phase. Okay, compared to another light source where the waves are all out of phase. Okay, if we think about a flashlight or a torch, okay, and shined it on this screen, it would look much different. Okay, and that's as a result of the fact that the waves are out of phase. And there are many different colors. And finally, these waves are parallel to one another, as you see here. So, in short, it's a very focused form of light. Okay? That's important because it's what makes LiDAR work the way it does. Okay. Now, for topography and forestry applications, that laser light tends to be in this infrared wavelength. Okay, there are lasers, there are LiDARs that operate at other wavelengths, but this is the wavelength that LiDAR tends to operate at for forestry applications. Next. Okay. The next component of the scanner gets at how exactly it works. Okay? You can imagine we have an aircraft like this one. It's flying along. Okay? And it has a laser pointed down at the ground. Okay? Now, the laser itself does not move back and forth. Okay? Sweeping the ground. It doesn't work quite that way. Because we don't want to move. This is a high-tech piece of equipment, and we don't want it moving. Okay? If we can help it. That just could lead to problems. Okay? So instead, what happens is, instead of having the laser move, a mirror is used. Okay? And it's the mirror that moves. The laser is stationary. It points at the mirror. Okay? The mirror moves in a particular pattern. And when that mirror moves, it creates the patterns that you see on the ground. Okay? And the mirror can move in different ways to produce these different acquisition patterns. Okay? And if I were to shine this laser at this mirror, holding it still but move the mirror, you can see what I mean. Okay? So it's the mirror that moves, not the laser. Next. Now, it's very important, very, very important, in fact, that we know at all times exactly where the aircraft is. Okay? Because if we know where the aircraft is in space, and we know its position in space, then we know where the LiDAR returns are coming from on the ground. But if we don't know this well, everything else falls apart. Okay? So there are two things that we need to know where the plane is in space and its position. The first is GPS, which you're all probably quite familiar with. All right? There needs to be a GPS reference station with line of sight to the aircraft at all times when it's flying, so that we know where the plane is. Okay? Next. The plane itself, however, needs to also have an inertial navigation system on board. Well, what is that for? Well, as you can imagine, as a plane is flying, it's being buffeted by the wind, right? It's not perfectly still. So we need to know the position of the aircraft at all times. And it's an inertial navigation system that provides those measurements of roll, pitch, and yaw. Okay? The exact movements of the aircraft. Okay? Next. Of course, there needs to be an onboard computer to put all this information together. The onboard computer records the returned photons of laser light, keeps track of the laser timing, keeps track of the angle that mirror is in at all times, records the GPS info, records the inertial navigation system info, It takes all of this and it converts the returns, the individual point returns, into x, y, z coordinates. Okay? Remember those point clouds I showed you earlier? We need to have an x, y, and z coordinate very accurate with each of those. And then, of course, it provides a real-time output display. Next. So, how exactly does it work? Well, it's really very simple. A LiDAR is just a tool for measuring distance, really. Right? And distance is measured by estimating the time it takes for a pulse of laser light to travel from the sensor to the target and back. Okay? And we need to know the speed of light for that. And because the distance is in two directions, down and back, we need to divide by 2, and we can get a distance measurement. If we know this distance, we can begin to measure the heights and structure of what's on the ground. Next. Next. Right, great. Okay. So, how are these returns recorded? Well, you can imagine the plane is flying, the laser is pointed at the ground, it's scanning using that mirror. Pulses of laser light are encountering targets on the ground. Could be trees, could be buildings, could be other structures. Okay? When the laser light encounters something, it's reflected back. Every time it encounters something, it's reflected back. All right? And the positions of those returns are recorded. The X, Y, Z positions of each return are recorded. All right? And it's those returns, when we put them all together, it forms that point cloud. Okay? Next. Here's our point cloud, right? So, all of these points are just as a result of those individual returns being recorded, and we have X, Y, Z positions of each of them. So LiDAR data is actually very simple. It's really just millions and millions of points where we know exactly where they're from. But when we put them together, we can begin to see very interesting and very useful patterns, particularly when we're talking about forestry applications. Okay. Next. Now, in the previous slide, we were looking at just 2 trees in the middle of a field, right? Well, this is an entire transect from a portion of the Yucatan Peninsula. And this is the point cloud that was collected. Again, this is displayed such that the tallest features in the image are red, the lowest features are blue. So ground is blue, tops of the trees are red, everything else is in between. You can see forest, okay? You can see a street, individual buildings, you can see a power line, you can see open areas, you can see a variety of different things. In great detail, okay, you essentially have a 3D representation of the landscape where the LiDAR was obtained. All right? And as you can imagine, the power in this is taking this point cloud and extracting useful information from it. And what the balance of my presentation is going to focus on is how we, as part of our work, have extracted information, forestry relevant information, from point clouds like this one. Next.
Sorry, I have a question.
Yes, of course.
If there is a lake in the middle of that point, also looks blue. For example, if there is some lake.
Yes, it would look, well, as I've represented it here, it would look blue. Because using this color scheme, it would have 0 elevation. But in general, yes, it would look like everything else at the surface. That doesn't mean you can't separate it from everything else. There are potentially ways to separate a lake from surrounding surface. Okay. Okay, now, we're going to spend today talking mainly about forestry and forest management applications, but it's important to appreciate that there are many, many applications of LiDAR. And when you look at one of these point clouds, you can begin to think about how many different applications there are, because there's so much data contained in this point cloud. LiDAR is being used for atmospheric measurements. It's being used to monitor glaciers and ice sheets. It's used to produce digital elevation models, looking at risk from landslides. There's all sorts of applications related to the hydrosphere, looking at water surface roughness, turbidity, shoreline and coastal change. There are urban applications in terms of urban planning. It's being used increasingly by archaeologists to identify, for example, beneath forest canopies, archaeological sites. And in fact, in some of the data that we acquired here as part of the MRED project, we found areas where if you just looked at the point cloud itself, you wouldn't see anything. But if you strip away the trees, you see structures beneath that are archaeological in origin. But obviously today we're focused here on the biosphere, particularly on vegetation, forest inventory, forest structure characterization. So that's what I'm going to be spending the rest of my time on. I'm going to be talking more about this, but there are many, many different attributes of forest structure that we can extract from LiDAR point clouds. And many of them we can do very, very accurately, more accurately than we can do with any other data. Whether it be biomass, basal area, canopy cover, tree height, stem density, ground slope, all of these are possible. And again, when you see these point clouds, it's not surprising that this can be done quite well with LiDAR. Next. All right. So I'm going to shift gears a little bit now. I'm going to talk more specifically about our MRED LiDAR initiative and potential applications of these data and data like them to the work that you all are doing here in Mexico. Next. Next. So just a brief outline. I'm going to first talk about the MRED LiDAR initiative. I'm going to talk about some of our accomplishments to date. And then I'll wrap up by talking about potential future applications to forest measurement and monitoring. So first, the initiative. What did we actually do? Well, let's present the timeline. In July 2013, Carto Data was awarded a contract through the MRED project, which is a USAID-funded project to acquire airborne LiDAR data at sites across the country. In December of 2013, the acquisitions began over Jalisco. The acquisitions continued through May of 2015. Took quite a bit longer, I think, than we expected because the acquisition team encountered a lot of challenges. Some of them had to do with weather. Okay, LiDAR has to be flown when the weather is good. You don't want to fly LiDAR when there are low clouds, when there's rain, when there's anything that the LiDAR pulses might encounter on the way down to the ground. Okay. There are also issues in terms of ground access in a number of locations. As I mentioned earlier, we need GPS line of sight to the aircraft at all times, and so a team needs to go out on the ground with a GPS receiver to collect that data, and in some parts of the country, access, of course, is difficult. So there were issues, and it took longer than we thought, but in June 2015, the completed data set was delivered. Next. All right, so now I'm going to take you through some of our accomplishments, all of our accomplishments really to date, where the LiDAR data is concerned. And the first one is that, of course, the acquisition was completed, and it was completed following input from a broad range of stakeholders. Government, including groups like yours at CONA4, academic institutions, local NGOs. We wanted to pool everyone's thoughts together on where we should allocate our resources in terms of acquiring these LiDAR data. Okay? And I'll talk a little bit more in a moment about some of the criteria that we were interested in related to where we put these specific sites. But it was important for us that we heard from everybody, because obviously we only had limited resources and we could only do this once. So we wanted to do it well, or at least as well as we could. So this is what the MRED LiDAR acquisition looks like. These black lines and black quadrants represent the actual acquisition, the places that were flown. Overall, 1,685 square kilometers of data were acquired through this effort. How did we go about identifying these particular locations? They seem to be sort of spread out, and they don't appear to have any real rhyme or reason to them. Well, first of all, we were interested in flying over existing locations where existing field data could be accessed, okay? So that includes INVIS plots, that includes other state-level forest network plots, that includes ecological field research plots, any place that we could fly where there was relatively current, relatively accessible field data that we could bring to bear on calibration and validation activities. Okay? So we talked to folks who were willing to share data. We also wanted to ensure that the acquisition was representative. What do I mean by representative? Well, we looked at layers of biomass, we looked at layers of forest type, we looked at layers of elevation, biodiversity, a number of different GIS layers to try to get a sense for the diversity of ecosystems in the landscape, and try to see how we could best capture those representatively with the LiDAR. We obviously had limited resources, but we wanted to do our best to capture as many different types as we could while ensuring that we were flying over places where data was accessible. So, a number of different criteria, and it actually took us quite a bit of time to put this acquisition plan together, but I think it was a really good process, and it was a process that we were proud to undertake. Next. Now, it's important to appreciate that the MRED LiDAR acquisition was not the only acquisition made in Mexico. There were several others, actually, some large and some small. The other large one was acquired a couple of years earlier, around 2012, by NASA. And it was called the NASA G-Lite sensor. And those flight lines are shown in blue. So you see the Carto data flight lines, the MRED flight lines are in black. The NASA G-Lite flight lines are shown in blue. So you can see when we put the two together, we have pretty good coverage throughout the country of the range of forest ecosystems. There are also other acquisitions that have been made, smaller ones, including one out here in Baja that we actually don't have access to, at least not yet. We hope to one day. I believe it was sponsored by the U.S. Forest Service. Eventually, we'd like to put all of these acquisitions together so that the community can make use of them collectively. Now, what you see in the background here is the distribution of conifer, INFIS, and forest management plots. You can see there are many, many plots, as you all know well, across the country. You can see the distribution of the LiDAR acquisitions relative to those plots. Now, obviously, in total, there are thousands of plots out there in the landscape. Of those thousands of plots, 671 fell beneath the two LiDAR acquisitions, the MRED Carto data and NASA G-Lite, okay? 671. Keep that number in mind because it's going to come up a little bit later on in the talk. Next. All right. The next accomplishment had to do with designing and implementing a data sharing platform. One of our objectives from the beginning was to make this data publicly available. Next. So we developed, as part of MRED, a spatial data sharing platform. The link which you can find here, where you can go and you can download these LiDAR data. Next. This is just zooming in on the Yucatan Campeche region acquisition. The LiDAR data set is divided into individual 1 kilometer by 1 kilometer tiles to make it easy to access. And I'll talk a little bit more about that in a moment. Now, the G-Light data, the NASA G-Light data, is also available online at this location. It's also available to the public. Okay. Now I'm going to talk about what we've done in terms of making the raw data and the derivative products available to the community, to the world. So coming back to this initial acquisition, okay, 1,685 square kilometers. Let's focus here for a moment in the region of Chihuahua. And we're going to next. We're going to take a close look right here. Next, if we zoom in, you can see the individual 1 kilometer by 1 kilometer tiles that are available online. Next, and we can see, and this is actually the online interface. We can see that there are a number of different data types available. Okay, for those of you that know GIS and remotely sensed data, you'll recognize some of these data. We've made available both the digital surface and digital terrain models. For those of you who don't know what those are, I'll explain them more in just a moment. We've also made available the hill shades of the surface and terrain models. And we've also made available the raw data. The raw data comes in a format called LAS, L-A-S. That is the format that contains the raw point cloud data. Next. Okay. So, there, yeah, thank you. So I want to give you a sense for what these data look like. Okay. This is a digital terrain model, and by itself, it doesn't look like much. You can see a little bit of variability here. You can begin to see some river valleys and some hill slopes. Okay, but it's kind of hard to get a good sense for what's there. Next. However, if we display it as a hillshade, which again, those of you that know GIS know what a hillshade is, we're essentially applying some shadowing to it. You can see what the terrain looks like in this particular region of Chihuahua. It's very, very diverse. Next. Now, this is the digital surface model. Now, if you recall the digital terrain model from 2 slides back, it looks virtually identical. All right? Doesn't look very exciting. But what makes the digital surface model different from a digital terrain model? Well, in the case of terrain, we're just looking at the bare earth. We've stripped off everything on top of it, including trees, including structures, everything removed, just the bald earth surface. Next. The digital surface model, however, leaves everything in. And here you can see this speckle pattern is actually due to the individual trees on these hill slopes. Okay? Now we're going to zoom in a little bit right here. Next. When we were collecting the airborne LiDAR data, we were also collecting orthophotography. So this is the ortho photo of that region. You can see there's a river valley. There's forest and hill slopes on either side. Next. Here is the terrain model. Now this is the bald earth model, no trees. Next. Here is the digital surface model. These are all individual trees. You can even see power lines. All right, and if we apply a color scheme to it, we can see taller trees in green, shorter trees here. These are orchards or small plantations in this orangey color. As I was mentioning, we can see power lines, we can see individual structures down here, you can see a lot of detail. You can almost, in this relatively sparse landscape, you can almost count the individual trees. Next. Okay. Let's take that same area and look at it in perspective point of view. This is that river valley that we were just looking at. Now, this looks like an orthophoto, all right? But it's not. It's also a point cloud, like the first slide I showed you in Oaxaca. This is a point cloud. All right, it's made up of 225 million points, and this is only 2 kilometers by 2 kilometers. So even this small area is a very large data set. All right? Now we're going to zoom in onto a region right here. All right, before we zoom in, we can display this point cloud in different ways. We can display it in terms of elevation. The elevation here ranges from 2,141 meters to 2,587 meters. Here are the lowest areas, of course, in the river valley, highest areas on top of the mountains. Next. We can also colorize it in terms of just forest height, tree height. From 0 to, in this case, about 40 meters, you can see the tallest trees growing in some of these moisture valleys. Now we're going to zoom in. Go back one. We're going to zoom in right here to a portion of this slope. Now this is about 40 meters by 40 meters, a relatively small area of the slope, and you can actually begin to pick out the individual conifers. You can see their shapes. All right, again here, 0 to 23 meters in height are these trees, and you can see they show up pretty well. You can almost count them in this point cloud. 200,000 points making up this relatively small, roughly 40 by 40 meter region. Next. Okay. One more. No, one more forward. Okay. Sorry. Yeah, okay. Now, I want to start, I want to switch gears a little bit, and I want to talk about how, as part of our research, we're using these data. How are we using these point cloud data to generate useful products, to generate useful information for forest measurement and monitoring purposes? Okay, what is our strategy? Well, first of all, I want to talk a little bit more about our philosophy, if you will. Oftentimes, what we're confronted with is a case where we have relatively sparse field measurements, okay? Let's think about the INFIS for a moment. The INFIS system is very robust, all right? As we saw in one of the earlier slides, we have plots, thousands of plots spanning the entire country, okay? But we also know how difficult it is to implement and maintain a system like that. Okay, it's very expensive. There are plots that are very difficult to reach. There are plots in remote locations, places, steep terrain, places that are inaccessible for other reasons. It's very difficult to implement and maintain an inventory that is truly representative of the landscape in a country as large and as diverse as Mexico. We struggle with it in the United States as well. Places like Alaska have virtually no inventory plots. As a result, they're beginning to look at technologies like LiDAR in large remote areas like Alaska to overcome the limitations associated with field inventories, okay? Now, next. What we're often interested in, of course, is taking these measurements, often sparse measurements, and saying something at the national level with them. Often we want to make maps, okay? We want to use these data to say something, to tell a story, to provide information at the national level. And as part of the work we do, we're often trying to make maps. Next. That typically involves using field data with satellite imagery, using some sort of statistical model, okay, to make the map. That's sort of standard practice. But there's a problem. There's a problem, and that there tends to be a data gap. What do I mean by data gap? I mean, we always wish we had more field data. We always, back one. We always don't have enough. We always wish we had more. We wish we had more plots here. We wish we had more plots there. We wish we had more plots in this forest type or in that forest type. There's always problems that we encounter when we're trying to do this. So, how can we overcome this gap? Well, this is where we look to LiDAR next. What if, as we've done in Mexico, and as has been done by other researchers and other practitioners elsewhere, we fly the available data with the LiDAR? Okay? We take advantage of the fact that we have this great system on the ground like INFIS, but we seek to extend it using really powerful data like LiDAR. So we actually fly the plots themselves. Okay? And in so doing, we not only collect data where the plots are, but we also collect data along the way where the plots aren't. Okay? So we're getting additional data, which is important. And then, next, we can use LiDAR as essentially a gap filler. Okay? Next. So instead of having one model, for example, we can have two. We can use the field data to calibrate our LiDAR acquisitions and make some really powerful maps of a range of different variables for these LiDAR acquisitions by themselves. Okay? But then, we can develop additional models where we take the results of the first model, okay, the maps of biomass, the maps of height that we have for the individual LiDAR acquisitions, scale them up using satellite data, all right, to make maps of the entire country, all right? So LiDAR ends up being used as a scaler from few sparse field data to wall-to-wall information, all right? You can imagine how powerful this is, particularly, again, in places that are difficult to access, okay? It provides a really important purpose with a great deal of value. And keep in mind, and we'll talk about this more later, LiDAR has a range of applications, right? Not just for forestry, but even beyond, right? But if we just focus on forestry, there's a great deal that we can do with it. I'm going to talk more about that now, next.
Wait, there is a question.
Yes.
Muchas gracias por la presentación. Tenía una pregunta referente a la diapositiva anterior. Si es posible mostrarla.
Yes.
Anterior.
One back. Okay, back. Back. One more. Yep, there we go.
Gracias. Está muy interesante el modelo. Usted indica que aún los datos del Inventario Nacional Forestal de Venezuela dice que es un sistema robusto. Está basado en un muestreo estadístico que le da soporte al diseño muestral general en el inventario, pero aún dice que no son suficientes datos. ¿En qué términos usted, digamos, hace esa afirmación? Yo entiendo que los sistemas, las comunidades forestales son discretas realmente. ¿Bajo qué argumentos indica usted por qué el inventario no es suficiente?
Okay, it's a very good question. First of all, during every cycle, are you able to measure every single plot, every cycle? That is the first question. Is that possible? Is it realistic?
No. hay un porcentaje de accesibilidad, aproximadamente 9%. 9%.
Okay.
Bueno, quizás a lo mejor valdría la pena indicar que el objetivo del inventario nacional forestal y cuál es el objetivo bajo el cual usted indica que no es suficiente.
Well, I'm arguing that inventories, field inventories by themselves, okay, they obviously have their objectives, but they are difficult to maintain completely over time because of inaccessibility issues, okay? Because of financial issues, because of all sorts of issues, they can be very challenging. Now, the other thing is that while an inventory is statistically representative, okay, there's a lot more that can be done with it in terms of producing national level data when combined with spatial remote sensing data. Okay? Because obviously, we know what's happening here, and we know what's happening there, but we don't know what's happening here, or here, or here. We don't truly know what's happening everywhere. We know statistically what's happening based on the inventory, but we don't truly know, right? We don't truly know. And we know how diverse the landscape is. And so I'm simply arguing that with some additional data, okay, and a model like this, you can know what is happening with some degree of error, with some degree of certainty, everywhere, okay? And during the course of my presentation and this afternoon, Alessandro's, I think we'll get there. We'll get there. So whereas my argument may not be as convincing right now, maybe by the end of the day, it might be, okay? But I understand, but Ali would like to make a comment.
So I think that one important consideration is, so what is the question? What is that you want to know, right? Because I agree with you that if what you want to know is the timber volume or the biomass for your country, the national forest inventory is perfect. That's what is supposed to do. And they do it very well, and especially in Mexico, it's one of the most advanced design and forest inventory that you can expect. So you will get your estimate when you measure the plots and you do the analysis of the forest plot, and that's done. Great, perfect. If that is what you want, but and that is based on a sampling approach, right? When you have a wall-to-wall map, you're not even talking anymore about sampling. You are talking about the census. Okay, if you speak from a statistical point of view, it's not based on a sampling anymore. It's like a census because each single cell is a single pixel. You have the entire population pretty much. And so with that information, you can do something more. If you will have an uncertainty, you will have an error. It's not perfect, but it might allow you to do something more. What can you eventually do more? For example, what if you want to report at the municipality level? At the municipality level, if you use your national forest inventory, you might have not enough samples. So you can always go back and add more samples. That's totally fine. But it's expensive. Some places becomes not accessible. So then you can do it, but your error is going to be pretty high because you have a small number of samples. Well, you can do sort of an integration between what a map will give you in a way to sort of add samples. and then there are many other applications when you have a map. I think it's easiest in one way to derive changes, for example, in biomes than using just forest inventories. Because the design of forest inventories is optimized to capture what it is there. It's not designed to capture the changes. I mean, changes are happening in like 2% of the country. I mean, so we can. This is a very interesting topic, and you know, I think we can talk more in the afternoon.
And so, as I was saying, throughout this talk and into Alessandro's talk, where we provide some of the examples of the application of this model, hopefully you begin to get a better sense for the power of integrating these different data types. Now, one thing I want to make clear, okay, is that we can't do anything here that we're going to be talking about today without a system like INFIS, okay? I've shown you some really pretty pictures of what we can do with LiDAR, okay? It looks great on the screen, okay? But we cannot make sense of that data without a system like INFIS. So this discussion here is not to say that INFIS is bad, LiDAR is good, okay? Not at all. It's simply to say that if we integrate these different data sources, we can do more, and we can do things better, okay? And we will always need forest inventory data. Okay, we have not gotten to the point, and I don't think we will get to the point anytime soon with remote sensing, where we will not rely, and rely heavily, on robust field inventory data for calibration and for validation. Okay? Yes, we can take satellite data, we can take LiDAR data, and we can use it to extend the INFIS, okay, so that we know what is happening in more places. But there is no substitute today for a system like the INFIS. Okay? It is critical. It is critical. Okay, next. All right, so let's remind ourselves of what we have here in Mexico. We have these two LiDAR acquisitions, some 4,100 square kilometers. We have thousands of field plots, including over 650 beneath the LiDAR. Okay? Next. Now, what is the breakdown of the plots that we have beneath the LiDAR? They're not all INFIS, okay, although INFIS represents the majority, 356 plots beneath the LiDAR. Okay? At least 356 as far as we can tell. But we have a number of other sources as well. Okay? We have field plots from some of the intensive sites. We have field plots from an MRED campaign that we undertook specifically to get more points in regions of higher biomass. Okay? We have some of the Forestry Research Network plots available to us. So we have a range of different data sources that we brought together here that constitute these 671 plots. Okay? 8 different data sources. Okay? A range of different plot sizes. Okay? So I show this simply to say that in this particular application, we were bringing together whatever we could find, okay, from a variety of sources, from a variety of groups that were generous enough to share their data with us. Okay?
Alex, para el estado de Chihuahua, ¿cuáles son los
Okay. For the state of Chihuahua, which are the results? Para el estado de Chihuahua, ¿cuáles son la fuente de los plots?
Well, some of these plots are from Chihuahua, and potentially some of these as well. These and some of these. The rest are from other places.
Right.
Okay. What you see here is the distribution of those 671 plots. Okay, the little black dots that you see here are the 671 plots. I have these plots superimposed on a map of ecoregions just so that you can get a sense for the diversity of the different ecoregions that are covered by the plots that we use. Okay, if we zoom in here on the Yucatan Peninsula, you can see in blue the carto data acquisition. Here in blue, you can see the G-Light acquisition in red. And there are plots beneath all of those flight lines, okay? And they're spread out across the country. Next. Now, in this particular application, our focus was on above ground biomass. All right, so for each plot, we wanted an estimation of above ground biomass at the plot level. And that's what you see here in this histogram. Okay? For all 671 plots, you have a value of biomass ranging from 0 to just over 600 megagrams per hectare. Okay? And you can see the distribution across those various ecoregions. Okay? So the goal, our first goal, was to generate maps of above ground biomass within the LiDAR acquisitions themselves. Okay? So within just the LiDAR acquisitions, make a map of biomass with these field data. So, not wall to wall, just for the LiDAR itself. Next. So how do we do this? How do we turn the LiDAR data into a biomass map? Well, you remember that the LiDAR data is made up of point clouds, like you see here. This is one of those 671 plots from our MRED high biomass field campaign. This particular plot's from Chiapas. These plots were 25 meters by 25 meters. This is the point cloud. All right, you can see in red the tops of the trees. You can see the distribution of vegetation in the canopy. This is looking down on the point cloud. So how do we take this and turn it into useful information that we can make a map out of? Okay, next. Well, this is what we do right here. Okay, this is very important. This is the key piece to the puzzle right here. This is a LiDAR profile of this point cloud. How do we get from here to here? Well, what we do is we take this point cloud, we separate it into bins from top to bottom, half-meter bins. Okay, half-meter bins, and we count. We count the number of points in each bin. All right? We plot the number of counts on this graph. All right? You can see we start here about 0, we go up to about 50 meters, which is the top. And when we look at the shape of this profile, we get a sense for the distribution of vegetative material from top to bottom. Okay? You can see up here in the middle of the crown, all right, we have the highest number of counts, and that's where we have the most vegetation material. Right? This is the ground right here. And this is the very, very top of the canopy here. Now, based on our field information, we know that there was roughly 300 tons of biomass in this plot. So, this profile tells us what 300 tons of biomass looks like using LiDAR data. All right? Now let's look at some other plots. Next. Okay. This is the same plot, same profile we just looked at, but we've added 4 more. We've added 4 more from Chiapas, Campeche, Durango, Oaxaca. Right? 5 different plots where we've taken that point cloud and we've turned it into that profile. Now, what I want you to just look at is the shape. Look at the shape, how it changes. Okay? And then let's look at this biomass value. Just over 300, 167, 117, 110, 7. And look at how the shape changes. All right? We have lots of area under the curve here, and we have high biomass. And as biomass decreases, you see how the profile changes. All right? So this profile, okay, is capturing the 3-dimensional vertical structure of the vegetation. And we use these profiles then, okay, to derive metrics that we can use in modeling. Because we want to now describe this profile mathematically, okay? So how do we do that? Well, you can imagine a bunch of different metrics that can be extracted from this profile. For example, the area under the curve, the height of mean energy. Okay, you can separate this into quantiles. Okay, you can figure out the maximum height, the height of this peak. There's all these different metrics that you can extract. There's hundreds of them that the community of researchers that have worked on this topic have come up with to describe this. They're infinite. Okay, they're very simple metrics. All right, next. These are just some examples. This is an idealized profile. Here's the ground peak. Here's the peak in the canopy. Here's the top. You can see these various metrics of height that can be used to describe. Question, yes?
Una pregunta, en la diapositiva anterior, ¿cuál fue el tamaño de las parcelas utilizadas en cada uno de estos estados?
So, this was from the MRED acquisition, so those plots were 25 by 25 meters. This is from the UJED research plots, and this was an IMPHIS plot. So these plot sizes are different than these, okay? And in these plots, we've accounted for that by normalizing the counts by area. Okay, we've adjusted the counts by the area so that the impact of area on these plots is removed. But they are different in terms of plot size.
El tamaño de la parcela tiene algún efecto en la estimación que se obtiene a través del aire.
It can if we don't account for it. Okay? We need to be able to account for it. All right? So we need to know what the plot size is, and we need to make adjustments for it so that it doesn't impart any error to the estimation process.
Otra pregunta. El tipo de vegetación igual tiene algún tipo de influencia. En este caso fueron los mismos ecosistemas o fueron distintos.
No, these are very different ecosystems. Okay, this is Oaxaca, Durango, Campeche, Chiapas. So these are in different ecosystems. Okay, and so if we go back one more, please. All right. So this ecosystem, right, this forest type is characterized by pretty large trees, very high biomass. All right, if we go up to Durango, forests are very different. The biomass on average is much lower. So yes, that absolutely has an impact on how much, the more vegetation you have, the denser the returns, okay? And that results in differences in what this profile looks like.
Muy interesante las diapositivas. Una pregunta, ¿el objetivo final es determinar la cantidad de biomasa? ¿Se considera de alguna manera la densidad de la madera en la contabilidad?
Okay, good question. So, the ultimate objective in the application that I'm about to show you is biomass. But at this stage, that doesn't have to be the objective, okay? Because we can use these profiles, we can use this information to map anything we want, okay? Obviously, you can see one of the things that LiDAR does best is measure height very accurately. Okay, and we can get height directly, okay, off of this graph. For example, it's a direct measure, essentially. Okay, but we can also use these profiles to estimate canopy cover, to estimate stem density, to estimate whatever attribute you might want, as long as we have good field calibration data, for example, from the inputs. Okay. What I'm going to show you is an example based on biomass, okay? And you asked about wood density. Well, from our field-based estimates, right, from our plot-based estimates, the allometric equations that are used to turn diameter and height into biomass also include, in every case, a wood density estimate. So wood density is accounted for in the field data side of the equation. So you might think of these plots as sort of the baseline information. And then we take this baseline information and we turn it into whatever variables we're interested in. Okay? All right, next. Okay, so we have to derive these metrics from those profiles. We have to turn those profiles into useful variables. All right, and these are some examples here. Next. Okay. Then what do? Well, we develop a model. This is a relatively simple, multiple linear regression model. It's based on 4 variables. 5 variables. 4 of the variables are derived from those LiDAR profiles. Okay? These first 4 here, okay, are derived directly from those profiles. And there are software packages of various sorts that turn those profiles into metrics. And as I mentioned, there's hundreds of them. Here we used a stepwise approach to select the 4 most important metrics, 4 mapping biomass. Additionally, we also incorporated ecoregion because we were trying to develop a model for the entire country at the same time. And as I showed you in the previous slide, and as you well know, there's a great deal of ecosystem variability across the country. We wanted to make sure we accounted for that in our model. So this is a relatively preliminary model. You can see it has some scatter to it, but it has an R squared of 0.74. And this requires a little bit of additional work, but I'm actually quite pleased with it, and I'm quite pleased with it because it is based on a number of different plot sources. It is based on a number of different plot sizes. It is based on allometric information from a number of different sources. There are a lot of things that are going into this model. Ordinarily, we would like to base a model like this only on one plot source, like the infus, for example. Okay, but we needed and we wanted to use as many different sources as we could. And of course, when you do that, that comes with error, potentially. All right? But in spite of that, this is a pretty good model, given everything that we brought to the table. Now, with this model, okay, we can generate a map of biomass within the LiDAR data. Next. Oh, this is just the same plot colored by ecoregion. You can see that there is really no discernible pattern in the model where ecoregion is concerned, which is a relatively good thing. Next. Okay, I want to give you an example now of how we map biomass. And we're going to focus right here. This is part of our acquisition in Jalisco. So focus right here. Next. All right. So for that particular location, this is what the orthophoto looks like. You can see a forested hillside here. You can see some agricultural fields. These agricultural fields are separated by hedgerows, by rows of trees. Here is the digital terrain model, okay, which is something we can get directly from the LiDAR. Okay. Very easily, we can derive digital terrain models from the LiDAR. Here is a map of canopy height from 0 to 18 meters. You can see the tallest trees are in these moisture valleys, shown here in green. You can see the hedgerows show up very nicely. You can even see different heights in the individual trees of the hedgerows. Okay, so lots of detail here. And then here's our map of biomass. Now in this example, we're mapping biomass at, I believe, 50 meters. Ultimately, we're going to map biomass at 30 meters, but this is actually a little bit coarser. Okay, you can see the individual pixels. This is much higher resolution. This is close to 1 meter. This is 50 meters, and you can see the relationship between the canopy height map and biomass. Where we have these hedgerows, you can see the biomass values. They range from 0 to over 100 megagrams per hectare. You can see where we have dense forest here, we have high biomass. Out in the middle of these fields, you can see where there's no biomass. Okay, you can see this patch right here where the trees are relatively short. We have low biomass. Okay, so you can see the relationship between height and biomass as we would expect. Okay, and we can do this for the entire LiDAR acquisition across the whole country. Carto data and the G-Light. Next. Here's an example of what that looks like for the Yucatan acquisition. Maps of biomass. You can see the individual plots that went into producing the model, the 671 plot model. Okay. So we can generate these relatively high resolution maps of biomass for the entire acquisition. Okay. And we can stop there if we want. Okay, if we want, we can just stop there. But as I discussed earlier, what we now are looking to do is using these maps as part of a second model to produce wall-to-wall data. Okay? And that's what Alessandro is going to be talking about this afternoon, the next step. Taking these results and turning them into wall-to-wall maps, where we have effectively, as Ali mentioned, a census of biomass. Okay? Next. All right. want to talk about a couple of other accomplishments as part of this initiative before I wrap up. In addition to acquiring these data and analyzing them and producing hopefully some useful products, we also conducted some training workshops, 2 of them specifically, one in Durango and one in Merida, in collaboration with the U.S. Forest Service. The purpose here was obviously to work with folks like yourselves and others in the country, academics, folks from NGOs, to better understand these data and how they might be applied in Mexico. Next. This is a workshop we held in Durango. Some 20 participants across 13 different organizations, including a number of government organizations. Next. Here was our workshop in Merida, 25% participants, again, a number of different organizations represented. Next. In addition to the training and the scientific analysis, we also engaged in producing some outreach products to make the more general public aware of these data. We designed and distributed fact sheets and infographics. Next. Here is an example of one of our fact sheets. Next. Here's an infographic we produced, again, describing for the general public what LiDAR is, how it can be used. Next. And finally, and this is what Alessandro is going to talk about tomorrow, he's going to talk about how we've used these data to generate estimates of biomass and biomass change wall to wall for the country. Next. Next. Not going to dwell on that slide because that's what Alessandro is going to be talking about. Okay. So now before I wrap up, I want to talk about some future applications. Question?
Sería tan amable, ¿podría regresar a la presentación al slide donde está la regresión?
Yes. Go back several slides.
La regresión lineal.
Further. Another one? One more.
They are so nice. The relationships.
I hope to make it better.
Wow, it's pretty good. Es muy buena. Tiene un coeficiente de correlación cuadrático de 0.74. Aquí aplican algunos filtros, bueno, entendí que los bullets aquí arriba, sí, filtras como los datos, ¿no? Primero que el 100% del retorno de la señal sea mayor de 3 metros. ¿Podrías explicar un poquito cómo filtras los datos y qué manejo le das a los eventos extremos? Which the management with the extreme events?
Okay, so let's go back another slide. One more. Okay. The key to working with LiDAR is first being able to generate these profiles, which is relatively simple. But then we have to turn this into useful information. We have to turn these profiles into variables. Variables, predictor variables, that we can use in a regression equation. Okay? And we call these variables metrics. Okay? They're metrics. And they are simply ways of describing what we see here. All right? Think of this as a function, and we want to describe it. So one variable might be the maximum height, the total height. And here it would be around 49 meters. Okay? Think of that as one metric, one variable. For this plot, 49 meters. For this plot, 35. For this one, 19, 22, and so on. That's just one variable. But we can come up with other variables. We can say, okay, what is the height of the first peak from the top? Here it's at 32. Here, if you consider that a peak, it's about 32 also. Here it's at 12. Here it's at 17. Okay? Now we have two metrics. One metric might be the area under the curve in each case. Okay? So that's a third metric. And there are hundreds of these. We can keep going. We come up with these different ways of describing what is here in this profile. Right? And those are variables. Those are variables that we can then use in a regression analysis. So we have a software that produces these metrics. And they're very common, they're in the literature, and there's literally like 100 of them. Okay? Now go back to the plot of the next one. So here we used a stepwise approach to select from among those 100 variables the ones that were most important, the ones that explain the variable. The majority of the variability in biomass across these plots. Okay? And here are these four. And some of them are a little complex. Okay? For example, the height 40, what is that? Okay, let's go back to the profile. Oh, forward. Yeah, right there. Okay? What is height 40? Well, height 40 is the height at which 40%, we see 40% of the returns. Okay, we can divide this entire profile into quantiles, we can divide it many different ways. But for example, height 40 is where we see 40% of the returns. So that's another metric. Okay, and like I said, there's many, many of these. All right, go back to the equation.
Which one?
This one. In some of these, it can get quite complex, mathematically speaking. This is all returns greater than 3 meters divided by all returns times 100. Okay? By itself, it doesn't mean much intuitively, but it's another way of describing that profile and extracting information from it. All right? So these were the four metrics that were deemed most important by the regression analysis, and those were the ones that we used to generate this model. Now, we're not always going to use these four, right? If we work in a different region, if we include more field plots, if we change anything about this, it's possible that these four might not be the same four. Maybe there'll be 6, and maybe they'll be different. It all depends on the calibration data, right? Depends on the calibration data. So this is one model, and these are the predictor variables associated with this one model. They're not always going to be the same, depending on the analysis we're running. If we change the inputs, if we change anything about the analysis, those will also change. Does that answer your question? A little bit? We can talk more if you like. So I want to spend a few minutes now talking about future applications. I've given you one example of what we can do with the LiDAR data, and this afternoon, Alessandro is going to extend that example. Okay? He's going to show us how to take these data and turn them into wall-to-wall information. Okay? But I want to emphasize, this is just one thing we can do with the LiDAR data. Next. So what else can we do? What might the future be of LiDAR data in Mexico? Well, as I've suggested, we can take these data together with INFIS, okay, and generate more information for more of the country, okay? Go from a sample to a census, as Alessandro described. Okay, that's one thing that we could potentially do. Second, next. Change anything. I've already shown you how we can use the data to extrapolate measurements to unsampled locations. This afternoon, like I said, he's going to do that for the whole country. And this, of course, is important when we're talking about remote and inaccessible regions. From a research standpoint, you can imagine there's all sorts of things that can be done with data like this, where forest structure and biodiversity is concerned. Okay? It's not just necessarily about mapping basal area or volume or biomass. Next. In terms of applications for RED+, okay, we can use these data to improve emission factors, again, because we're going from a sample to a census. Next. We can do things like evaluate logging and degradation impacts in various parts of the country with data like this because we have such detailed information about the forest structure. And we can do things like explore biomass change, net emissions estimation. Again, Ali will talk more about that. So in summary, I would just say that while airborne LiDAR data can be expensive to acquire, when combined with high-quality field data, it is the highest quality 3D remote sensing data now available for forest measurement and monitoring applications. It's being used all over. These applications are numerous. The U.S. Forest Service FIA program is now using it in places like Alaska to supplement their forest inventory system. You can see based on these point clouds the sort of information that you can extract, okay, from these 3D models, these detailed 3D models. It's very powerful. It's not a replacement for the INFIS system, but it can be used together with the INFIS system to provide more and better information at the national level for all sorts of forestry-related applications. And so as our work together potentially moves forward in the context of MRED, we would like to think about how we might be able to work with you to integrate LiDAR data of the sort that we now have for Mexico. And we have great LiDAR data for Mexico across the entire country if you count these various acquisitions. It is a very representative sample in terms of LiDAR. And so we'd like to think about moving forward how we could work together, potentially to do some tests, okay? To think about what can be done to demonstrate further the utility of LiDAR data for conifer, for forestry applications. And as I mentioned, there's a whole range of them, not just biomass, right? So with that, next. I thank you for listening. Thank you for all your good questions. And I appreciate your attention. And if you have any more questions, I'd be happy to take them.
Thank you. I was thinking, estaba pensando en la última próxima diapositiva el futuro de esta tecnología del LIDAR. Y solamente, pues, quizás, si tiene conocimiento de que se pretende lanzar un satélite para estimación de biomasa. ¿Cuál es el futuro en términos de disminuir los costos de las adquisiciones de imágenes LIDAR hacia el futuro? ¿Cuáles son las expectativas?
Okay, that's a great question. Well, first of all, in part of your question, the earlier part of your question, you mentioned a satellite being put up for biomass estimation. Can you? I'm not sure I understood you correctly. Can you tell me a little bit more about what you were referring to with the satellite?
Entiendo que es una cooperación entre la NASA, las agencias espaciales de Japón, de la Agencia Espacial Europea y otras iniciativas que tienen el objetivo de lanzar un satélite que pueda estar midiendo la biomasa.
Yes, that is true. That is true. There is a mission that's being developed. It's actually based on radar technology. Okay, so it's a different sort of technology from LiDAR. And for large areas, at least in theory, it will be able to produce estimates of above ground biomass. Now, this is a relatively new, this will be a new satellite, new data based on relatively new technology. So it's hard for me to speak to what my expectations are for that particular system. I certainly think it will be valuable. How valuable, I can't say. Will it be able to produce detail like this? No, it's certainly not designed for that. It is not a LiDAR, and it's not going to give you anything like this at all. But for large area mapping, I suspect it will be quite useful. Okay? I think when it comes to talking about satellite data versus LiDAR data, particularly airborne LiDAR data, or LiDAR data collected by UAVs, I think one of the powerful aspects of airborne LiDAR data and potentially UAV LiDAR data is that you have the power to collect the data wherever you want. We will always have airplanes, and we will always have LiDAR sensors to put on those airplanes. The powerful aspect of LiDAR UAV, this talked about this satellite data wherever you want. It will have a lifetime. Okay? It will be launched, let's say 2020, and maybe it lasts for 5 years, maybe it lasts for 8 years, and during that period, of course, you can make use of that. But this is a technology that certainly provides better information. It does cost money, but it is in your hands to spend that money how you wish, in terms of you can design your own sampling strategy. You can fly as much of the country or as little of the country as you like. These days, unfortunately, even when it comes to satellite data, not all of it is free anyway. A lot of it is, but not necessarily all of it. So what LiDAR gives you is a lot of flexibility. Okay, a lot of flexibility that you don't, and the possibility to think longer term. Because I think airborne LiDAR technology will always be there now. Now we have it, and as long as we have airplanes that will fly, we can collect it. So there's nothing stopping us 10 years from now, 20 years from now, and it's probably only going to get better. Whereas satellites, there's more uncertainty there. They might be here today, but they might be gone tomorrow, we don't know. So from an investment point of view, I feel like LiDAR technology, in the context of an organization like Conifer, where your mandate is to monitor Mexico's forests and to do that as well as possible, I think there's little question that this technology provides you with the best tool to do that. Now, I understand it's costly, but I think there are ways, of course, to manage that cost. So I guess that's what I would say. I'll let you anything to add on that. Question?
Bueno, hay algo que no estoy entendiendo completamente. Creo que es parte de la exposición que va a hacer Alessandro Bacchini como parte de la presentación del mapa de cambios de biomasa. Pero yo no sé si nos pudieran adelantar ahorita un poco, al menos de manera muy general, los principios de cómo se genera este mapa, en base a mi siguiente pregunta. Estos modelos de regresión que nos mostraron, entiendo que relacionan los datos de campo con los vuelos, los transectos básicos. Pero, ¿qué pasa con lo que no ocurre en LiDAR? Que creo que es el siguiente paso para hacer el mapa wall-to-wall, que es con las áreas que están fuera de los transectos LiDAR. Yo creo que esto que nos mostraron es cómo relacionan un punto del inventario nacional forestal con el transecto y el área que está fuera del punto, ¿no? Pero ahora, lo que está fuera de lo que cubre el LiDAR, supongo que forzosamente se deben utilizar variables de sensores remotos, no sé, el NDVI, o qué otros variables o criterios utilizan. ¿Cuál es el principio general? Porque entonces siempre vamos a seguir dependiendo de los sensores remotos. Ya, digo, es como claro.
Okay, good question. And yes, Alessandro is going to make everything clear. I know it. But in the meantime, you're absolutely right. I talked about this piece, just as you described it, taking the field data, relating it to the LiDAR, and generating maps at the scale of the LiDAR transects. Okay? Now, what we want to do is make wall-to-wall maps. We want to have information everywhere. Okay? We want a census. So yes, we are reliant on another data set. Okay? And our philosophy there is to always try to use freely available data that we have an expectation is going to be around. Okay? So, Ali's going to talk to you about two examples. One using MODIS data, and one using Landsat data. All right? Landsat data, of course, is our longest record, going back to the 70s. I have no reason to anticipate that it won't extend into the future. MODIS is also a platform that has been highly reliable, coarser resolution, but also a scale of data that I think we might be able to count on having in some form freely available into the future, at least we hope. So, we're researchers, we don't want to pay for data either, okay? So, what Ali's going to do is talk to you about how we now take the biomass estimates from the LiDAR transects, okay, and use those now in a different model as calibration data, okay? Generating another model that relates these data, the result of this process, okay, generates a new model to predict in all those other unsampled locations, in all the places where the LiDAR didn't fly. So it's a two-step scaling process. Field to LiDAR, LiDAR to wherever we want to go, the globe, if you like. So that's the process. And yeah, he will fill in the details. I know there's great anticipation. Other questions? In the back, yes, sir.
En tu experiencia,
bueno, ahí en la oficina estoy trabajando con la parte de las áreas de difícil acceso. El problema que yo tengo con las áreas de difícil acceso es que no están distribuidas, digamos, de forma homogénea en el país, sino que por diferentes condiciones tienden a agruparse. Entonces, llegan a formar grandes regiones, por ejemplo, la mitad de un estado, o dos parcelas, ¿no? En tu experiencia, ¿cuál ha sido el tamaño y las dimensiones de las parcelas de calibración que tú usas para el LiDAR? Y si tratas de distribuirlos de cierta forma dentro de estas áreas.
Good question. Show that, please. Okay, this you might be familiar with. Yep. So I think, can you show it? I'm trying. Oh, sorry. So I think, and you can tell, you know this better than I do, but I think the areas in yellow are some of the trouble spots. Is that right? Yeah. Okay. So let's take this example, right? Obviously, when we flew the LiDAR, we didn't have access to this, okay? And we weren't therefore able to take advantage of this. But you could imagine a strategy, okay, a focused strategy, wherein we rely on INFIS everywhere else, but in these places, we use more of a LiDAR strategy, okay? Now, hopefully, in these inaccessible areas don't contain entire forest types, for example, or entire ecoregions. Because, for example, this is quite a large area, right? Because we need calibration data, all right? And if we can only fly LiDAR data here, but we can't go into the field, we still need to be able to use calibration data from outside of the region to predict what's going on in the LiDAR. So you can imagine, though, all right, designing a strategy around these inaccessible areas where inside of the yellow boundaries, the focus is on the LiDAR. Everywhere else, the reliance is placed on the INFIS. And you use the INFIS where you have it. You use the LiDAR where you have it. And you use the INFIS to calibrate the LiDAR in the places where you don't have the field data. So I don't know if that answers all the questions, but if there was another part to it, please repeat it. But I can imagine a strategy like that.
Sí, nosotros ahorita estamos tratando de generar un modelo utilizando datos de campo para llenar esos vacíos de información. Entonces, supongamos que, no sé, Chihuahua, por ejemplo, supongamos que todo es bosque de pino. Utilizamos datos de otros estados que también son de bosque de pino para imputar al interior de Chihuahua. Utilizamos hermanos como variables ambientales. Y si hay buena correlación, digamos, asumimos que la información que está afuera va a ser lo mismo que está dentro de Chihuahua.
Absolutely.
Entonces, ahorita el siguiente paso que me gustaría hacer es, con la información que tienes de biomasa, tratar de utilizarla como un calibrador y ver si hay alguna correlación con lo que estamos generando nosotros.
Right, right. That would be very interesting.
Ahorita lo estamos tratando de hacer, digamos, a nivel país, considerando que es un esquema nacional. El siguiente paso es tratar de reducir la incertidumbre e irnos a una escala regional. ¿Por qué? Porque a nivel nacional el estrato es homogéneo, pero a nivel regional ese estrato realmente es heterogéneo. Entonces, por ejemplo, ese es el caso de los manglares, a nivel nacional se tratan iguales. Pero si tú te vas a una escala regional, esos manglares realmente son bastante heterogéneos. Entonces, la idea es tratar de predecir primero nacional, regional, y tener una serie de parcelas distribuidas, ya sea dirigidas o no, para utilizarlas como calibración y reducir, digamos, los costos de ir a campo.
You know, that what you describe, what you're already doing, is exactly the sort of strategy I think I'm talking about. Trying to use the data that you have to smartly overcome these limitations imposed by accessibility and so forth. And so what I'm suggesting is simply the possibility of adding a LiDAR component to it. And you can see with the LiDAR data, obviously, the range of different variables, the range of different information you could extract from it in these places where you can't go on the ground. And so I would simply offer to consider integrating airborne LiDAR data into what it sounds like you're already doing, essentially. Because I think what you described is exactly the way to try to overcome this problem. And I have no doubt that with what you're doing already, you're going to have some level of success. The question is, can you do even better? And I think you probably can with the LiDAR. Yes.
Quería agregar un punto al comentario de Sergio. En este proyecto de lanzamiento del satélite para medir biomasa, se requiere información de campo que tenga tanto la parte del inventario, de los inventarios forestales, como vuelos de LiDAR o vuelos que permitan generar una mejor aproximación para generar estos modelos. Entonces, aquí en este taller que tuvo lugar el año pasado, aquí lo recomendable es que tú tengas un censo total de toda la línea que se vuela con el LiDAR o con otros sensores. De manera, ellos hablan de super sites, o sitios de muy alta calidad de información que te permita generar una muestra de primero generación del modelo y un super site para validar el modelo. En líneas generales, no sé si el INFIS como tal no aplica porque no tienes el censo total de todo lo que vuela el LiDAR. Y tiene que ser como sitios de 100%, básicamente, y tienes que levantar absolutamente todo para poder generar esta información que te permita llegar a estos modelos. Bueno, esa fue la experiencia en este taller de NASA que Probablemente, no sé si quiera agregar el doctor Ward alguna información.
If you like, with who is involved? With who are you working on this project from the NASA side?
Están involucrados varias personas, no recuerdo exactamente su nombre, es un apellido hindú, y están trabajando en coordinación con la agencia japonesa, la agencia espacial europea, NASA y otras iniciativas de medición de biomasa a nivel mundial. Pero le puedo conseguir el nombre, porque justo ahorita no lo tengo a la mano.
So I just would like to briefly add, so these missions, yes, so there are a couple of missions actually that are based on radar data, and this is one, the biomass mission. But I think before that mission will go up, there is going to be, if everything, if they don't change it, a LiDAR mission that's called JEDI. JEDI, that it's a US-based initiative. And this is a LiDAR mission. And this is going to be free. The data will be free. And the data are supposed to be of very good quality to do biomass work. Even before that, there is going to be ISAT-2, that is another LiDAR satellite from NASA that is also going to be free. That while in the very dense tropical forests, there are questions how well it's going to work, but for many parts of Mexico, it could work pretty well. So, but all those initiatives, they will require field data. There is no satellite that right now, without calibration, with field data, is able to tell you what the virus is. And LiDAR is a way to try sort of to minimize the cost and the issues with accessibility of the field data to provide a lot of calibration data. Because when you fly the LiDAR, that's street. You can have so many samples out of that street. So what you can think about is design a LiDAR flight strategy that is based on a stratified sample approach that will sample all the different vegetation type structure that you have in the country. You don't really need wall-to-wall. I mean, wall-to-wall LiDAR for the countries like Mexico.
And just following on what Alessandro was saying, I mean, this is essentially a stratified approach. We stratified it based on our own strata, okay? But, for example, you could imagine developing your own stratification of the country, your own acquisition strategy for the country that incorporates that map of inaccessibility, for example, okay? So that the acquisition is perhaps more focused there in places where you can't get to easily with the influence, okay? So you can think about taking something like what we've done, which is pretty good where forest is concerned, and further tweaking it to meet your own specific agency monitoring needs, okay? Optimize it from a cost standpoint, optimize it from an information gathering standpoint, optimize it from any number of different points of view to get out of it what you need. Other questions? Not? I hand the floor back to MC.
Thank you. Pues bueno, creo que lo que acabas de plantear, Sergio, es de importancia para nosotros, para pensar en el futuro cercano, ¿no? Esta campaña de adquisición de datos LIDAR, el kilómetro cuadrado costó $400. Si pensamos, o sea, es alto el costo, pero si pensamos en la solución que va a proveer al INPI para hacerlo más robusto, creo que la inversión no es mucha, ¿no? Obviamente habría que hacer un cálculo a nivel país y ver cuál es el costo-beneficio de extrapolar este tipo de estrategias. Pero pues uno de los mensajes claves de esta iniciativa es que haya una discusión interna en la CONAPOC sobre la viabilidad, si le encuentran sentido este tipo de tecnología, y pensar en una estrategia conjunta en el corto plazo. ¿Ustedes ven esto como una posibilidad viable? ¿Les interesa? ¿Creen que no es la solución?
Bueno, o sea, digo, a expensas de que haya una discusión mucho más fuerte al interior, lo que sí te puedo decir es que, digamos, o sea, tenemos que llenar vacíos de información, ¿no? O sea, el parte del trabajo que estamos realizando es también ver las tendencias de inaccesibilidad a nivel nacional. Entonces, estamos haciendo un recuento desde que iniciamos en el 2004 hasta la actualidad, porque las causas de inaccesibilidad han sido diferentes, ¿no? Entonces, lo que estamos tratando de hacer es que teníamos una clasificación muy general de inaccesibilidad, pero ahorita la estamos subclasificando. Entonces, esa subclasificación nos va a poder permitir decidir si realmente, o sea, no se hizo un esfuerzo inicial para poder entrar, o si realmente no se puede entrar. Entonces, ya de ahí partimos para definir las áreas que realmente son inaccesibles. Entonces, el siguiente paso es ver cómo están distribuidas. Pueden ser 2 parcelas en medio de un mar de accesibilidad, o realmente una agrupación de parcelas, sí que puede llegar a ser medio estado, un cuarto estado, por ejemplo. Y con la tendencia podemos ver que a lo mejor en el siguiente ciclo no va a poder ser medido. Entonces, a partir de ahí, lo que estamos haciendo es explorar diferentes iniciativas. Entonces, una iniciativa primero era trabajar con los datos tabulares, los datos de la base de datos, y ver cómo podemos llenar ese vacío. La siguiente es cómo con esos datos de campo podemos cruzarlo con sensores remotos o otro tipo de tecnología. Y si, digamos, la correlación sigue siendo muy buena, mi intención es tratar de reducir costos, en el sentido de enviar brigadas a campo y tratar de usar más sensores remotos en combinación con lo que tenemos en campo. Y la idea es que estas parcelas a lo largo del tiempo sean nada más parcelas de calibración. Y tal vez manejar parcelas temporales en donde, digamos, dentro de un área inaccesible, la dinámica es muy alta. Sí, porque la idea es que estas parcelas de calibración permanezcan en el tiempo en áreas que son homogéneas o que no cambian mucho, digamos. Y tratar de buscar esas estrategias, ¿no? Entonces me llamaba la atención los vuelos, porque algunos sí cubren las zonas que tenemos, pero hay otras donde no. Por ejemplo, el caso de Chimalapas, que está entre Chiapas, Oaxaca y Veracruz. Entonces es un gran vacío. Entonces lo que estábamos planteando era terminar este ejercicio tabular y nosotros mismos ir al campo y tratar de remediar alguna de las parcelas que están ahí dentro para tratar de fijar precisamente unas posibles líneas de vuelo. Y también definir qué tan heterogéneo o homogéneo es ese estrato, ¿no? Lamentablemente, no tenemos mucho conocimiento, bueno, en lo personal yo no tengo mucho conocimiento sobre el AIDA y pues, me estoy apoyando básicamente en el área que con Miguel. Y estamos tratando de utilizar, de ver qué variables también de campo podemos utilizar en combinación con el AIDA. Y pues ese sería el ejercicio a discusión, ¿no?
¿Podrías comentarnos un poco más sobre esta subclasificación de las razones de inaccesibilidad?
Sí, mira, por ejemplo, cuando inició el inventario, básicamente decían, hay 2 tipos de inaccesibilidad, social y natural. Entonces, social podría ir desde no me dieron permiso hasta la presencia de guerrilla. Natural, desde la pendiente estaba muy empinada, por ejemplo, 45 grados, 100%, hasta una inundación, un incendio forestal bastante grande, o simplemente una distancia, no había caminos, por ejemplo. Entonces lo que hicimos fue crear una subclasificación de 12 tipos. Básicamente, a grandes rasgos son cuestiones físicas, cuestiones sociales. Las sociales las subdividimos en sociopolíticos. Ahí está todo lo que es guerrilla, narco, conflictos agrarios, cuestiones de idioma, usos y costumbres. Y también, por ejemplo, tenemos la clasificación natural va desde zonas de riesgo volcánico, incendios forestales, inundaciones o crecientes, por ejemplo. ¿Sí? En ese sentido es lo que estamos tratando de clasificar. Y lo que hacemos es que realizamos un análisis más profundo para ver qué tan certera es la información, y eso lo cruzamos con conocimiento experto. La ventaja que tenemos es que, por lo menos algunos compañeros y del área de nosotros, ya recorrimos todo el país. Entonces, realmente sí conocemos cómo está la situación, la tendencia. El último criterio es el criterio experto, básicamente.
Y entonces, en este sentido, cabría la posibilidad de generar estrategias distintas dependiendo de estas subclasificaciones. Obviamente, en el tema político no hay mucho que hacer, pero en el tema de idioma, por ejemplo, o conflictos agrarios, pues sí pueden haber estrategias conjuntas, ya sea que se les capacite a estas comunidades para que ellos mismos hagan estas medidas, etcétera, ¿no? ¿Tú consideras eso viable para el próximo ciclo alimentario?
Sí, digo, sin sonar pedante, o sea, realmente aquí la clave es el contacto que tú tengas con un tercero. Esa es la clave, ¿no? Por ejemplo, hay zonas donde Chimalapa, hay zonas donde Conafor no entra. ¿Por qué? Porque es gobierno y representa una institución que no se quiere. Pero hace poco logramos entrar porque tenemos un contacto, sí, que a su vez nos contactó con otra persona y tuvimos acceso a uno de los lugares más difíciles dentro de Chimalapas. Entonces, digamos, creo que todo tiene que ver con la forma de comunicación con la gente y ubicar ese contacto. Y incluso, por ejemplo, en zonas sociopolíticas donde hay presencia de guerrilla, o sea, todo tiene que ver ese contacto tercero. Entonces, si ese tercero nos permite entrar y negociar, por ejemplo, levantar una parcela de calibración, sí, para nosotros ya fue un logro. ¿Por qué? Porque sabemos, o sea, conocemos el área y podemos decidir exactamente dónde poner esas parcelas. Y ya cuando definitivamente no tenemos ese tercero, o definitivamente ya ese tercero nos dice, sabes que aquí no se puede, entonces ya podemos establecer otra estrategia.
Gracias. ¿Algo querés comentar algo, Fernando? ¿No? ¿Alguien más que gustaría compartir alguna inquietud sobre las distintas áreas en las que trabajan y cómo podríamos también solventar vacíos de información con este tipo de tecnología?
Incendios, por ejemplo.
Es muy interesante para nosotros, sobre todo para lo que nos sirve es para lo que son los inventarios de combustibles. Sin embargo, lo de incendios es muy dinámico, necesitamos información muy particular. Entonces, sí es una gran área que se cubre y es un área importante, sin embargo, gran parte de nuestros incendios ocurren en el resto de la República. Entonces, sí, nosotros necesitaríamos mayor cobertura. Nos puede servir mucho para lo que son los inventarios de combustibles, para saber exactamente, como te miden los diferentes estratos de altura, nosotros podríamos ver, digamos, la facilidad de que un incendio se convierta rápidamente de copa o no, dependiendo de los estratos que las imágenes de vida nos muestran. Sin embargo, como los incendios son casos muy particulares, requeriríamos información muy particular de zonas que no están incluidas. Por el momento lo que aprecio, no soy mi compañero.
Bueno, implementando nada más lo de Tania, en el caso de incendios forestales, ahorita con el cambio de supresión en el manejo del fuego, lo que nos interesa sobre todo es medir cómo se comporta ciertos ecosistemas después del paso del fuego, ¿no? En este caso, por ejemplo, con el inventario, que ya son remediciones, estimaciones LIDAR, más adelante podríamos ver cómo se están comportando los ecosistemas a nivel región. sobre todo ecosistemas dependientes, sensibles, independientes al fuego. Y todo eso, pues bueno, nos va a ayudar a justificar, de cierta manera, los tratamientos que se le pueden dar a ciertos ecosistemas con la aplicación del fuego. Pero sí, sería un trabajo mucho más, en todo caso, mucho más regionalizado, sobre todo por tipo de ecosistemas.
Sí, para el área de sanidad, pues estamos trabajando ahorita lo que son los mapas de riesgo y estamos básicamente, trabajamos con reflectividad. Entonces, por lo que yo entendí de LIDAR, pues maneja estructura, ¿no? O sea, no maneja cambios de coloración, por ejemplo, en la vegetación, que es lo que nosotros trabajamos básicamente o requerimos, ¿no? Porque cuando, por ejemplo, hay el ataque de un descortezador, que es el más visible, pues inmediatamente se detecta ese cambio en la vegetación, pero es un cambio en coloración, ¿no? Entonces, igual, pues tengo la duda, no sé si el sensor, bueno, lo mida, mide ese tipo de cambios o está basado solamente en la estructura, como mencionaban en la altura, ¿no? Se podría también a lo mejor utilizar en cuanto a la evaluación después de un tratamiento, o sea, el comportamiento de la estructura de la vegetación después de la aplicación de un tratamiento de una plaga o una enfermedad.
So, I think that if you are interested in colors, there are cheaper and easier ways to derive. Pretty much any optical sensor is able to give you what I think you need. You don't need to do that. And the data are free. And now with Lancet 8, there are very good quality data at the resolution that for a model like yours, I think could be enough. If you want to go higher, you can always go to Spot, you can go to Rapida, and things like that. If such a measure of like changes in colors. But I'm curious to know a little bit more. I mean, why do we need changes in colors? I think in one way, you know, a plague, a disaster, is something like that. I don't know why you need to change colors and not changing tree density, changing vegetation type, changes in the vegetations, in the structure of the vegetation. And it's just like, is it, but because when you talk about color, it's really like more green or less green, right, for the vegetation.
Bueno, el cambio de la coloración es como un síntoma, más bien es un síntoma preventivo, donde todavía se puede realizar algo, el control. Ya un cambio en la estructura, pues ya son los árboles muertos, ¿no? Ya es el ataque pues completo, ¿no? Ya no hay mucho que hacer. Entonces la detección de un cambio en la coloración del follaje es temprano, pues, o sea, es el ataque en un determinado lugar e inmediatamente ir para que el mismo no se expanda, ¿no? Es ir y controlar. Entonces, eso es lo que es preventivo, pues, por así decirlo. El otro ya sería demasiado tarde.
¿Y en la actualidad qué insumo utilizan para detectar el color?
Imágenes. Y lo que menciona, o sea, el Lancet está libre,
Bueno, ¿alguna otra intervención?
Bueno, primero que nada, quiero agradecer por esta excelente presentación y por los alcances que ha tenido este trabajo. Al respecto, quisiera consultar cuál es el costo de poder hacer este tipo de vuelos de una manera rutinaria, con la cual podamos aprovechar esta información y estos métodos para ciertas áreas que, por ejemplo, de inventario donde no puede acceder, ¿no? Donde no puede acceder las brigadas de campo.
Bueno, como comenté hace un momento, para esta adquisición, el costo por kilómetro cuadrado fue de $400. Fueron $700,000. Es bastante dinero. Lo que hemos estado pensando, incluso platicando a veces en alguna ocasión con el ingeniero Betancourt, consistiría en que la CONAFOR haga un convenio de cooperación con la Sedena para en sus aeronaves montar los sensores. Y mientras ellos están patrullando en distintos sectores del país, pues que de paso se utilicen los sensores, que obviamente tendrían alguna utilidad, ¿no? Más allá de eso, abaratar el uso de la tecnología, bueno, no sé si tú tienes una alternativa, pero creo que de momento no es algo que sepamos, ¿no?
I think it's difficult to sort of provide you with a quote, simply because at the end of the day, the cost varies a great deal by how much area you want to fly, what the distribution of those areas are, because at the end of the day, if you're hiring somebody to do it, or even if you're doing it, even if another, say, government agency is providing the aircraft, it comes down to fuel costs. And it comes down to how do you efficiently manage those costs. And that really relates to the flight plan. So it's difficult to provide just sort of a ballpark estimate. I would like to think you as CONAFOR, you as the Mexican government, would be in a position to, for example, negotiate a much better deal than we as MRED and USAID would be able to. So I would like to think that for you it would be much more inexpensive than for us. So I don't know that necessarily what we pay is a good starting point for thinking about it.
Thank you.
Bueno, pues muchas gracias por sus comentarios, por la presentación bastante ilustrativa. Y estamos muy bien en la agenda. En 20 minutos sería la hora del almuerzo. Entonces no sé si lo podríamos adelantar o tomamos 20 minutos de descanso antes de la comida. Sí, perfecto.
¿Puedo preguntar? El software, ¿cuál es el software que utilizaron para realizar los reportes? Porque bueno, nosotros, como Sergio comentó, pues hemos estado trabajando más o menos para ver cómo poder trabajar los datos LiDAR, porque ya vimos, bueno, de hecho en la página donde estaban estos vuelos, estaban, ya no pudimos acceder, no sé si se cayó el servidor, no sé qué pasó, lo están actualizando, algo pasó. Incluso yo me puse en contacto con personas de Catadata para que me pasaran los vuelos, la fase nada más la guía, para poder nosotros identificar los conglomerados donde necesitábamos nada más descargar información y poder trabajar, ¿no? En este caso, quisimos hacer un ejemplo en Jalisco, en Mazatlán. Pero después de ahí ya pudimos acceder a la información. Sin embargo, también lo que mostraron como los gráficos donde se nos decía la altura y la cobertura también vegetal y demás, pues esa parte sí nosotros no la hemos explotado, no hemos sabido cómo generar esa información y sería importante pues nosotros conocer qué software utilizaron para poderlo generar y pues también igual para saber cómo modelan o con qué software trabajan realmente para hacer los modelados del LiDAR y nosotros pues poder también hacer algunas prácticas.
Sobre la plataforma, sí. Cambiaron las reglas de seguridad de Google Drive, donde estaban hospedados los datos. Por eso dejó de funcionar. Y en una semana exactamente los tendremos de vuelta. Ahorita ya estamos acomodando el servidor, pero tenemos limitantes de espacio. Pero en una semana tendremos todos los datos. Ahorita están los de Jalisco y Oaxaca disponibles. Y pues sobre esta construcción de capacidades, yo creo que podemos pensar en un taller específicamente para la CONAFOR, en donde vayamos ya al uso de los paquetes que utiliza Wayne, justamente para darles esta otra parte de análisis. ¿Tendrían una idea de cuántas personas estarían interesadas, tendrían el conocimiento necesario para recibir el taller?
Yeah, we held 2 of these workshops previously, as I indicated in my presentation, and you know, if there was interest within going forward, we were absolutely you know, willing to hold a tailored focus workshop just for Code staff. We'd be happy to do that, and then at that point, you would be introduced to the software, and you'd be able to learn more about how to do some of these things that you saw on the screen. So that's a conversation that we can have.
Hola, tengo una pregunta sobre cuál es el área mínima o el área óptima para minimizar el error al hacer la estimación de bioma.
So that, I mean, that's a multi. There are many parts to that question. I mean, I think it very much depends on the details. It very much depends on. Well, first of all, are we talking about LiDAR? And then it depends on what the ultimate objective is. Are you just trying to map biomass within the LiDAR acquisition, or are you going to try to map an entire state, an entire country? How much field data do you have available? There's a whole long list of questions, I think, that have to be answered before I could give you a specific answer to your question. I guess my response is there's no one answer to that question. It very much, the devil's in the details, as we say. It very much depends on what those details are. Where are you mapping? What are you mapping? How big is the area? How much field calibration data do you have? Do you need? All of that, when you put all that together, that impacts the error. So once you know all those things, then you can start thinking about the error. But yeah, there's no sort of one easy, simple answer to this question.
Otro comentario, cuando se extraen los valores de los puntos de captura de los árboles, lo que es copa, tallos, también los puntos de sombra, los píxeles, cuando se mandan al modelo solamente se llevan los que son arriba, los que y se eliminan los que mapean en el suelo, ¿no? Entonces, al hacer el ajuste del modelo, está la estructura del área, que sí están tomando el área como una superficie plana y eliminando el factor de la pendiente. Me pregunto si al hacer la regresión por lineal múltiple, podremos incluir ahí la variable pendiente.
Porque al principio lo estamos eliminando, ¿no? Pero creo que sería bueno, ya estamos metiendo bosques, existe la pendiente.
Absolutely, absolutely. We, in our model, we have removed it, okay? But we have normalized the data, we've removed the effective slope from the point cloud. But yes, it's another sort of ecosystem level variable. You could absolutely include slope in the model. You could include elevation in the model. You could include climate data like precipitation. There's any number of other variables that you could include in that model to improve it. That, as I said before, that's not necessarily the best model. That's the best model I have today to show you. It's not necessarily the best model that could be produced. And slope is one variable of a list of variables that could be used. Absolutely.
Independientemente de las variables a utilizar y el número de variables, el concepto de determinación, ¿cuál consideras que es un óptimo, ¿no? O que pasa el umbral aceptable como modelo?
Yeah, that's a good question. What is the optimal R-squared?
Académicamente se dice, no, pues que sea mayor de 95, ¿no? Mayor de 90, pero prácticamente ahora tenemos un punto 70, entonces en la realidad eso no existe, ¿no? Pero creo que sería bueno tener un parámetro de parte de los expertos, a lo mejor un punto 80.
Well, I mean, really, I would say that based on literature and sort of our experience, we usually tend to be happy when we have an R-square that is higher than 0.75. Okay, if it can be above that or around that, we think that you explain quite a bit of the variance in the variable. I think today with good field data and LiDAR and the techniques that are available, you would be around 0.8. I mean, we see it from the class data. We got a 0.8 from the LiDAR data. This is just a preliminary result, and I'm quite sure that it will improve as we start really looking at like the different functions and how we can do this and so on. So between 0.7 and 0.8 is good. If you get 95, something is wrong, probably. Okay? I'm not sure if I could be happy if I get a 95. I personally, when I showed the class with the 0.8 for the tropics, I was told that was impossible, that was wrong. So sometimes if you get a high values, just
I think in the case I showed you, as Alex said, that was a preliminary model of 0.74. I'm pretty sure with some additional work we can get that to 0.8. And if I get it to 0.8 or above 0.8, I'll be quite happy. I totally agree. If I saw 0.9 or 0.95, my first inclination would be to think, okay, I did something wrong. Where did I do something wrong? Because, particularly in this case, which is a very real world case, bringing in multiple data sources, multiple plot sizes, multiple forest types across a very large country, data collected by many different people. You start thinking about sources of error. You very quickly start to manage your expectations from 0.95. When I first ran that, I would have been happy with the 0.6. And I was actually quite surprised and quite pleased to get 0.74. Because, data like this are they're messy. It'd be one thing if I went out myself and measured every plot of those 671 plots it measured every tree and did the allometric conversion myself, et cetera, et cetera, et cetera. But, you know, when you have many cooks in the kitchen, you know, who knows how the meal's going to turn out. So, yeah, I totally agree. 0.75, 0.8, that's pretty good. That's pretty good.
De acuerdo con eso. Perdón, Carmen. Voy a hacer mi pregunta, en el comentario. Desde el punto de vista de software, ¿cuál es el costo computacional de analizar este tipo de entrada de datos? Porque son ya, miles de millones de registros, ¿no? No sé cómo lo podríamos medir, si por una hectárea, cuánto tiempo tarda el procesador en darnos esa información, o por hectárea, o cómo se.
Well, that's actually a very good question. And it's not only a question that you're obviously asking, but it's actually a question that we're asking because we're struggling a bit with this data set ourselves. And in the next couple of weeks, we are going to explore and do some tests of what it will cost us to move this data into the cloud using maybe Amazon Web Services or some other platform to see what it will cost to do it in the cloud. Because at our center, using the computing resources we have, it's not so much costly in terms of money because we own the computer, but it's costly in terms of time because the computer is not powerful enough, fast enough. So to process these data in the way that we need to process them, it's taking weeks, not hours or minutes. So I don't have a good answer for you right now, but we actually need to come up with an answer, and we will have a better one in a couple of weeks, I think. Because we're going to do some testing with Amazon and get to the bottom of that. Because ultimately, this type of data needs to be processed in the cloud, in a cloud-based system. That's no doubt the future, and that's where we think we need to go. And I think, speaking yesterday, there are some efforts within COM4, I think, to do some processing in the cloud.
Yo tenía, bueno, era agregar un comentario al tema de cuánto es aceptable el nivel de regresión. Aquí es complicado porque realmente los modelos ustedes tomaron los datos del inventario nacional forestal de y pues hay algunas consideraciones que tenemos en el término de que pues solamente se miden individuos de más de 7 centímetros de diámetro y también hay una cantidad de biomasa en el estrato herbáceo y arbustivo que es una aproximación también pequeña en el inventario, pero la imagen, cuando toma la imagen, se integra toda la información existente en cada una de las parcelas. Entonces, yo creo que el punto 7 es muy bueno, en base a que pues, hay muchas variables que están jugando en el modelo. Y no sé si ustedes consideran también, cuando se hace la medición en campo, existe una contradicción de la medición por las pendientes. Y aquí estamos trabajando con modelos de superficie. No sé qué tratamiento también para darle en este tema.
I absolutely agree. The minimum diameter measurement, for example, in a given plot, I mean, that's absolutely another source of error. That adds to the list, and it's a long list, and so I agree. When you start to consider all of those,
yeah, a model like this starts looking pretty good, absolutely. Because there are many sources, and many of these sources, like that one, we can't remove. There's no way to remove that. It's error that we have to accept in the model. As I mentioned previously, we are able to remove the effect of slope on the point cloud data. Now, as far as the effect of slope on the size of the plot itself, that is not something that we're considering in this map. We've not taken account for that source of error. So that's also
A mí me gustaría regresar al tema del tamaño de la parcela. Esto es un ejercicio que en un sitio de monitoreo intensivo, en Felipe Carrillo IV, se hizo una prueba para poder identificar si un mayor tamaño de muestra mejoraba las estimaciones con aire. Y bueno, en ese contexto quisiera también comentarle que el sitio de monitoreo intensivo de Felipe Carrillo Puerto, que se encuentra en Quintana Roo, cuenta con 32 conglomerados tipo I. Sin embargo, ese conglomerado está siendo manejado por investigadores, bueno, no manejados, sino también se trabaja de manera conjunta con investigadores del CICI. Y bueno, ellos tienen un especialista en sensores remotos. Y entonces trataron de identificar si al aumentar el tamaño de la parcela se mejoraba este proceso. Y buscando utilizar la información de las parcelas de este sitio de monitoreo intensivo, cambiaron ligeramente la configuración del inventario. Originalmente, una parcela del inventario nacional forestal de suelos está conformado como por 4 subparcelas. Y esas 4 subparcelas tienen una superficie de 0.4 hectáreas. Con fines de poder implementar la edad, hacer una estimación con la edad, los investigadores decidieron incrementar el área de la parcela central de 400 a 1000 metros. Y esa modificación estimaban que les podía ayudar a generar ese estudio con aire. Y entonces argumentaban que 400 metros cuadrados iba a ser insuficiente para poder hacer este análisis. Y después de esto, de hacer esa modificación, encontraron resultados que fueron positivos, ¿no? Un incremento de 400 metros cuadrados hasta 1000 metros resultó que podían utilizar mejor esta información. Y de ahí, pues, mi pregunta entre que si el diseño actual del inventario nacional forestal sería adecuado para poder generar ese tipo de análisis con la ayuda.
You're saying it would be. Or are you asking, or are you saying? I guess I don't know. I don't know the answer to that question. And I guess I thought that was what they were trying to answer with that study. I mean, it wasn't a question that we were trying to answer in this study, nor is it a question that we could answer. Because, to do that, we would need a controlled study of the sort that they conducted there, where they looked at the same place at varying plot sizes. This is a very different study where we're basically just bringing in data of different plot sizes from wherever it is, and using it in a model. So this research here was not designed to answer that question. My feeling is, however, that yes, the images are adequate for calibrating this type of data because it's such high resolution data. I mean, there's nothing more high resolution than LiDAR. So yes, my feeling based on my experiences is that the size is adequate. But unfortunately, this particular study can't definitively answer that question.
I just like to add that the most important things is that what you measure in the field is going to be consistent with what the LiDAR is sensing. Okay, and one of the major errors that you see when you do the calibration between field data and the airborne LiDAR data is actually the case in which you have a big tree that is on the edge of your field plot, where the log, the timber log, is inside, but half of the canopy is also outside, or actually vice versa. The log, the timber, the trunk is just outside, but you have half of the canopy that is inside of your plot. Okay? So in that case, when you go in the field, you will not measure the tree because it is outside. But the LiDAR is sensing a big, tall object inside of the plot. Okay? So there is going to be a discontinuity between the information that you collect in the field and what the LiDAR is seeing. So that is one source of error that is actually quite difficult to deal with.
And across large areas, we assume that.
So the reason because having larger plots helps is because over large area, the risk of having trees in and out sort of start to compensate, right? You have as many trees, you have one tree out and probably one tree in. I mean, you start to compensate that. And again, and the other source of error is when the field crew is calling a tree out of the plot or in of the plot when it's not. And if you have a small plot, when you report it to the actor, you multiply that error by how many times, right? So those are few considerations that you have to go through when you think about what the right size.
Bueno, pues si no hay más comentarios, solo cerrar diciendo que como parte de los productos de la Alianza México Verde estamos generando unos portafolios temáticos de cada una de las estrategias y este portafolio pues estará listo en un par de meses y se me ocurre, bueno, la intención es que el Centro de Excelencia nos ayude a difundir este material y se me ocurre que pedir apoyo al centro para pues, dar este entrenamiento específico a la CONAPOR. Creo que es algo que ustedes podrían coordinar de forma interna si es que la discusión apunta que es necesario y pues con las facilidades que tiene el centro lo veo totalmente viable para el portal.
Gracias, Manolo. Pues sí, lo vamos a ver hacia el interior, pero yo creo que sí puede haber mucho trabajo que hacer y pues que nosotros con gusto facilitamos para que pues, lo veamos aquí en el interior.
Gracias. Pues gracias a todos, la comunidad está lista y venimos en hora y media continuar con la presentación.
No, yo no me he separado de ahí. ¿Qué es lo que vas a hacer? ¿Lo vas a poner en pausa, cortinilla? Pausa, no para Vamos para el 1. Otra, pues no deja un letrero con la hora de la vuelta que diga. Deja un letrero que diga la hora que